what is the purpose of sophisticated terminology such as diffeomorphisms? Is it to intimidate the listener, bully the listener into believing that you are very smart? No. Language exists to serve as a shortcut to aid thinking. We are now going to define these terms, diffeomorphisms and local diffeomorphisms. This will enable us to talk about situations quite freely and in a concise manner. These definitions are motivated by the conclusion of the inverse function theorem that says that if a CK smooth mapping, the derivative of such a mapping, if it is non-singular, then locally the map is invertible and the inverse is differentiable. So we are going to introduce the notion of diffeomorphisms, which is the global version of the conclusion of inverse function theorem, and local diffeomorphism, which is the local version of the same. So you can concisely describe the inverse function theorem as saying that if the derivative map is isomorphic, then the map is a local diffeomorphism. So it sounds fancy, but it serves as a nice shortcut, an easy way to remember, plus it simplifies our thinking. So let's make the definition of diffeomorphism and local diffeomorphism. Definition: let U, V be subsets of E, be open sets. We say a map F from U to V is a diffeomorphism, or rather CK diffeomorphism, if first of all F is CK on U, second F is bijective, and 3 F inverse is CK on V. So it's this notion of a CK diffeomorphism is clearly just the global version of the conclusion of the inverse function theorem. You say that two open sets U and V are diffeomorphic if you can find a CK smooth diffeomorphism, a CK smooth map whose inverse is also CK smooth. So we will generalize this notion of diffeomorphisms to more general sets than open sets quite soon after we introduce the notion of manifolds. As I said, the conclusion of the inverse function theorem is local. You do not get a global conclusion. I have asked you to come up with a counter example. So let's make the local version of this definition. We say F is a local CK diffeomorphism. Is a local CK diffeomorphism if for each x in U we can find a ball bxr, and this r really is not independent of x, so let me just call it brx, a ball which is contained in U such that F restricted to bx Rx is a CK diffeomorphism, onto F of bx Rx. Okay, so what this is saying is we say that the map F is a local CK diffeomorphism if for each point we can find some small ball on which F is a diffeomorphism globally. So near any point it's going to be a local diffeomorphism. That's the conclusion of the inverse function theorem. So let's just summarize the conclusion of the inverse function theorem with this newfound terminology. If, or let me put it in a red color, if F is such that dfx is an isomorphism of vector spaces, of course, then then F is a local diffeomorphism on U. So if for all x in U, F is such that dfx is an isomorphism, then F is a local diffeomorphism on U. Again, please think of a counterexample to the conclusion of the inverse function theorem being a global conclusion. It's not true that even if dfx is an isomorphism at all points of view, it is not at all true that F is going to be a global diffeomorphism. Okay, so I kept saying that the definitions that I have made now, I kept saying that we have this conclusion. But if you recall, we just proved the case in the inverse function theorem. We just proved the case when F is a C1 map, right? We did not really talk about the CK smooth case. So far, actually, what I have written down in red is not technically correct. What I can really say here is that if F is C1 smooth and if dfx is an isomorphism, then F is a C1 or local C1 diffeomorphism. That's all we can say. We really don't have the CK conclusion as of yet, though I said that we have it. That's because I'm going to prove it right away. This is a corollary of the inverse function theorem. It's not that difficult to prove. Corollary: if F is CK smooth in the statement of the inverse function theorem, so the statement, exactly the same statement, except now we are assuming F is CK smooth, then the map G, again refer to the statement of the inverse function theorem to understand what this map G is, then G is also CK smooth. In the proof of the inverse function theorem, this G we have shown is actually going to be a C1 smooth map. Now the assertion is that it's a CK smooth map. Okay, how does this proof go? Recall that dgy is nothing but df at the point g of y inverse. This was one of the conclusions of the inverse function theorem. The derivative of the inverse is nothing but the inverse of the derivative. Okay, now our hypothesis is that the partial derivatives of the components of F exist up to order k and are continuous. This is essentially our hypothesis on the map F, saying that F is CK smooth means look, all the coordinate mappings are going to have partial derivatives up to order k, and all these partial derivatives are continuous. Now how can we use that? Well, we now move to matrices. So the entries of the Jacobian matrix, recall the Jacobian matrix is nothing but the matrix of partial derivatives. It is nothing but the matrix representation of the derivative map. So the entries of the Jacobian matrix of dfx comprise the partial derivatives of f1 to fn, where f is nothing but f1 to fn. These partial derivatives are all C k minus 1 smooth by hypothesis. Because the functions f1 to fn are ck smooth, the partial derivatives have to be ck minus 1 smooth. Okay, Now, the Jacobian matrix of G of dg, or rather here itself it's not the Jacobian matrix of dfx, that's not the correct way to say it. The entries of the Jacobian matrix of f at x. The Jacobian matrix is nothing but the matrix of partial derivatives, which is nothing but the matrix representation of the derivative. It doesn't make sense to say the Jacobian matrix of dfx. That makes no sense. So in a similar way, I must say the Jacobian matrix of G at the point y is df at the point g of y inverse. This is the conclusion of the inverse function theorem. I am writing this again. Okay, this means each entry of the Jacobian matrix of d g y consists of a rational function involving the partial derivatives of f1 to fn taken at the point g of y, right? So how do we evaluate this df g of y inverse? Well, you already know what df is and you know how to invert a matrix. It's just you will have to divide by the determinant of that matrix and take the cofactor matrix or whatever. I really don't remember. You have to take the cofactor matrix of the various, blocking out the ith column and the jth row and taking whatever. You will have a better idea what the cofactor matrices are. So when you actually think about this, what you're essentially doing is each entry will have some polynomial function of the various entries divided by the determinant, which itself is a polynomial in the entry. So this is going to be a matrix, each of whose entries of this matrix involves a rational function with the denominator not 0, because that's part of the hypothesis. This matrix df at the point g of y is invertible. Okay, so the entries of the Jacobian matrix, again I made the same technical error, of g at y. So the Jacobian matrix of g at y consists of rational functions involving the partial derivatives, and the denominator is the determinant, which is far away from 0. Okay, now what does this say? This means the entries of the matrix of dgy consists of ck minus 1 smooth functions. Why is it the case that the entries of dgy consists of ck minus 1 smooth functions? Well, note that the partial derivatives of f1 to fn are all ck minus 1 smooth, that we have talked about repeatedly, and these partial derivatives are going to be evaluated at the point g of y. So far we have got g is just a c1 smooth function, so it doesn't seem obvious that dgy, the entries of dgy, is going to consist of just ck minus 1 smooth functions. Plus remember that there is a denominator involving the determinant, and that function is also going to have a g is going to play a role there also, because the determinant is going to be evaluated at the point g of y. Therefore it's not really clear that the entries of dgy consists of ck minus 1 smooth functions, but we can prove this by induction. Okay, we can prove this by induction. Well, I mean, the base case is already done. We have already shown that G is C1 smooth. That bit is already done. Therefore, the entries of the matrix DGA is going to consist of continuous functions. So the base case is done. Assume that G is no, the assumption is not on G. Assume that the result, the claim is true for 1, 2, 3 ... r minus 1 less than k. Okay, that means we have shown that the entries of DGY are all C r minus 1 smooth. Okay, so one correction, I have to assume that r is less than k, not r minus 1 less than k, because our hypothesis is that G is a CK smooth mapping. So the entries of DG we have to show is CK minus 1. Okay, so we have now shown, that means not shown, we have now by induction hypothesis G is CR minus 1 smooth. In fact, it's CR smooth, sorry about that. It's CR smooth because we are assuming that by induction hypothesis that the entries of DGY are all CR minus 1 smooth. Okay, but we just said that the entries of DGY consists of a rational function evaluated at g of y, and this is not just any old rational function involving partial derivatives of f1 to fn. But the partial derivatives of f1 to f1 are all ck minus 1 smooth, and we are evaluating at a CR smooth function. The composition of a ck minus 1 smooth function and a CR function is continues to be CR smooth. That's where we have assumed that R is less than k. So net conclusion is that the entries of DGY are all CR smooth. Therefore G is CK smooth by induction. Okay, so there is really nothing happening in this proof. Just writing it out just complicates the whole thing. Just think about what is happening. Think about how the Jacobian matrix of F is going to look. Think about how the Jacobian matrix of G is going to look. Think about what happens when you take inverse, and this result should be fairly obvious. Okay, so we are now going to give a basic application of the inverse function theorem to polar coordinates, and that will conclude this video. So a basic application. The rest of the course is really an application of the inverse function theorem, so I do not want to focus too much on artificial numerical examples involving the inverse function theorem. You should work out one or two. They are there in the exercises, but I mean, other than getting a feel for what is happening, they're not going to really give you insight into the inverse function theorem. But it's important to work out at least one or two, just to make sure that you understand the mechanics of the inverse function theorem. So the application is polar coordinates. So let U subset of R2 be the set of points R theta with R greater than 0. Okay. Define f from U to R2 by R theta maps to R cos theta, R sin theta. Okay, so this is nothing but transforming polar coordinates into usual Cartesian coordinates. The Jacobian matrix, a simple calculation will tell you that this is nothing but cos theta minus R sin theta, then R cos theta. Okay, and this will just be R into cos squared theta plus sin squared theta, which is equal to R, which is greater than 0. So the Jacobian matrix is going to be greater than 0 at all points R comma theta. That means that this map F is a local C infinity diffeomorphism. You can extend the previous result Ck smooth to k equal to infinity in a straightforward way. So this essentially shows that this transformation from polar coordinates to Cartesian coordinates is a local C infinity diffeomorphism. You can actually write this down somewhat explicitly using arctan functions, which you would have definitely done in a basic course on multivariable calculus. But without knowing, I mean, I am not familiar with how to write this down correctly. I mean, I have done it several times in my life, but if you ask me to do it instantly, I'll probably make a mistake. But nevertheless, the inverse function theorem tells you that abstractly this map is going to be locally invertible. So that's the basic application of the inverse function theorem. You are going to see the more deep applications in the next video, where I talk about the implicit function theorem and then use the implicit function theorem to talk about manifolds. This is a course on real analysis, and you have just watched the video on diffeomorphisms and local diffeomorphisms.